Internal energy and work. Internal energy is one of the most fundamental concepts and quantities in thermal physics. Earlier, we saw that pressure and temperature can be related to the average kinetic energy of the molecules in an ideal gas. In an ideal gas, the total kinetic energy of all the molecules is called the internal energy, represented by a capital U. On the AP Physics 2 equation sheet, they have the equation for the average kinetic energy of one molecule. 3 halves kT, where K is the Boltzmann constant. Just multiply this by N, capital N, the number of molecules, to get the internal energy of the gas. So the internal energy, U, is equal to the sum of all the kinetic energy in the gas, which is equal to the number of molecules times the average kinetic energy of one molecule. So we take this equation from the AP2 equation sheet, plug that in here for the average kinetic energy of a molecule. So then we get this and this. So the internal energy can be represented with NK or NR, depending on if we want to deal with moles or molecules. The internal energy of an ideal gas depends on temperature and the number of moles of gas. Remember, capital R is the universal gas constant. This equation is not on the AP2 equation sheet. You have to derive it using the equations on the previous slide. An increase in temperature causes an increase in internal energy. Since we have nRT in this equation, we can also replace nRT with PV, since PV equals nRT. The state of any thermodynamic system can be described with the internal energy. The internal energy of a thermodynamic system can be changed in two different ways: adding heat, Q, to the system, or doing work, W, on the system. In 1845, James Joule presented his paper on the mechanical equivalent of heat. He was the first to discover that doing work on a system increases its temperature. A simple example of a thermodynamic system is a quantity of gas enclosed in a cylinder with a movable piston. Consider the work done by the piston as it pushes down, compressing the gas. Suppose that the cylinder has a cross-sectional area A and the pressure exerted by the piston is P sub piston. The force exerted by the piston on the gas is force equals pressure times area, since pressure equals force over area. When the piston moves down a distance delta x and the pressure P is constant, the work W is work equals force times displacement. So the force would be pressure times area times displacement. And since A times delta x is equal to the volume lost inside the cylinder, so here we have cross-sectional area A, and we go down a distance x, so this right here is the volume lost. When you multiply those two together, you get this volume in here that you've lost. So therefore A delta x can be replaced with change in volume. And here we have an important equation. The work done equals the pressure times the change in volume. Remember from AP Physics 1 that if the displacement is in the same direction as the force, that is positive work. Therefore, when the piston moves down, the gas volume decreases. So the work W done by the piston is positive. The force exerted by the piston is down, the displacement is down, they're in the same direction. That is positive. In that same scenario, the gas is doing negative work since it is exerting an upwards force while there is a downwards displacement. If instead the gas pushes up on the piston, causing an expansion, the work done by the gas on the piston would be positive, since the displacement would be in the same direction as force. As the piston is pushed upwards, the piston is doing negative work, since the displacement and the force are in opposite directions. On the next slide, there's a summary chart to help make this clearer. When solving problems with work, it is always useful to think very carefully about whether that work is positive or negative. Alright, so to summarize, here we have a gas being held in by a piston that can move up or down. During an expansion, the gas particles are pushing up and the piston is moving up, which means the gas is doing positive work and therefore the piston is doing negative work. During a contraction, when the piston is being pushed down, the piston is doing positive work since it's moving down while the force is pushing down. But the gas particles during that same action are pushing up against the displacement, therefore the gas is doing negative work. On the AP Physics 2 equation sheet, they have the following. W equals negative P delta V, where W is the work done on a system. You might be wondering, why is there a negative sign? As you can see, W on the equation sheet stands for the work done on a system. In the previous example, this would be the work done by the piston. If there's a positive change in volume, so here's the gas, positive change in volume means the piston is being pushed up by the gas, which means the work done by the gas is positive. However, that means that the work done by the piston is negative. So if the change in volume is positive, the overall work done by the piston is negative. So that's why there's that negative sign in there. Just make sure to think about any problem that involves work to verify if you need the negative sign or not. This relationship can be represented as a graph of pressure as a function of volume on a PV diagram. So here we're going from state A to state B, and what's happening? Well, this is an isobaric process where the pressure stays constant, but the volume is increasing. So the work done equals the area underneath this curve. Remember, work equals P times delta V. Delta V is this distance here. P is this distance here. So if you multiply those together, you actually get the area in this rectangle here. In an expansion, the work done by the piston is negative, and the work done by the gas is positive. The gas and the piston do the same amount of work, but one is negative, the other is positive, and what you're looking for will depend on the problem. The work done equals the area under the curve on a PV diagram. In a compression, so here we go from B to A, because that's the direction the arrow is pointing, the volume is getting smaller. The work done by the piston is positive. So here is our piston, the gas. So if the piston's pushing down and the displacement is also down, that means the piston is doing positive work, and the work done by the gas pushing back up would be negative. But the work done is still just going to be P times delta V, the area in here. So step 1. Calculate the amount of work done. Step 2. Determine whether it is positive or negative depending on what the problem is asking for. The system always pushes outwards. In this case, the gas inside the balloon is the system. The surroundings always push inwards. In this case, that's the air outside the balloon pushing inwards. What is the work done during the process shown in the PV diagram on the right? This is an isovolumetric process. The temperature and pressure are increasing, but the volume is staying the same. So you can see that there is no area underneath this line. If there's no change in volume, there is no work done. You can also see that on the graph here, there's no area under the curve. There is no work done. Here's an example problem. The state of an ideal gas is changed in a closed path from A to X to B to Y and then back to A. During the entire process, how much work is done on the gas? All right, let's go through this piece by piece. So from A to X, there's no work done. Remember, work is pressure times change in volume, and there is no change in volume from A to X, therefore no work done. From X to B, there's an expansion, right? So we start with a volume of V, we end up with 2V. We've doubled our volume, which means the gas has done positive work, the piston has done negative work. So the gas is expanding, therefore the piston is doing negative work. The area under this line here is all of this. That's the area under this line. So that is the rectangle here. What is the area of that rectangle? Well, this height here is 2p, and this width here is 2v minus v, which equals 2pv. And since the work is negative, it is negative 2pv. Now I'm going to erase all that. All right, clean slate. Next piece. From B to Y, no work is done. There is no area underneath this curve. There is no change in volume. From Y to A, the gas is compressing. Therefore, the piston is doing positive work. Now we can just take the area under the curve, the area under the line, and we have this rectangle right here. So the height is P. The volume change is V minus 2V, so our final minus our initial. So we're going to have negative V as our volume change. Since this work is positive, it will be P times V. So you add those together. So negative 2PV from X to B plus PV, the work done from Y to A, gives us a final work done by the piston of negative PV. The piston does more work to go from X to B since there's greater pressure during that process. Rules of a thermodynamic cycle. You must start and end in the same place. The change in internal energy over the whole cycle is 0. The net work done is the area inside the cycle. In a clockwise cycle, more negative work is done on the gas than positive work. Therefore, the net work will be negative. If you move counterclockwise this way, more positive work is done on the gas than negative work, and therefore the net work will be positive.